Hello, so today we are doing this problem called Strobogrammatic number. It's a little bit hard to pronounce it, but essentially it's a number that if we rotate it 108 degrees, so it looked upside down, then we find the same number. And so we want to write a function to determine that, right? So basically, for example, 6, 9, if we rotate it, it will give us this 180 degrees. It will give us, maybe I can find an image that kind of explains this better after rotating. Yep. So for example here, 1961, if we rotate it, we kind of find 180 degrees, we get the same one. So you can see here, you can see it rotated. So that's basically the idea here. Now, one interesting thing to look at is just look at a set of numbers that are that have this property. So if we look at this sequence with a couple of them, these are some of example of these numbers. You can notice some pattern. So we have 0, 1, 8. Those are already like if you rotate them 180 degrees, you still have the same. It still looks the same. And then we have 6, 9, 8, 8. So one thing you can notice is 1, 1 and 8, 8. So basically, if it's the same occurrence, the same number of occurrence of 1 and 8, and it's only those, then that's a strobogrammatic number. One other thing you can notice is that if you have 6, 9 or 9, 6, so if the two sides at the symmetric position are 6 or 9, then the number has that property. For example, here 619, it has 6 at this position and has 9 at this position. And so if you rotate 8 degrees, kind of 9 becomes 6 and 6 becomes 9. And the ones, since just when you rotate them, each one of them becomes just the same number basically. You can see that with 9866. So that's the insight to solve this problem. So let's just get into it and solve. So let's see here. So what does that mean? That means is that if we have a number, let's say with these digits, let's say these couple of digits like this. So we want the numbers at each symmetric positions, which is, for example, just I and n minus I. So I, and if n is the length, then this number here should be n minus I minus 1. So each number in its symmetric position, which means this one and this one, and sorry, this one here, and this one, and then this one, and then this one, and this one. Those are the symmetric kind of position. So these needs to be either the same, so numbers in symmetric position should be either the same and are 0, 1, and 8. Because if we look here, if the number is not 0, 1, and 8, that means if we rotate it, even if it's 6, if we rotate it, we will not get the same number. So that does not work. So we need it to be either the same and are at the same position, or one of them is 6 and the other is 9, right? So that's kind of what we can deduce from, can observe from the examples, right? So what can we do then? So let's just check this. Let's check this in code, right? So what we are going to do is first just take the length and then go through a half, like take just this half and then check the values here with the values in the other half, which are in the symmetric position of I. So in order to take that half, we're just going to divide by n and then we are going to add +1. Why? Let me show you why we need to add that +1. Because if we take, let's say, if we take 3 divided by 2, that's just 1.5. We can't really iterate to 1.5. So that's why we are doing this. But this gives us only 1, which means that we will check only if we had like this, we would check only 1, which means we'll check only the 0 position and this one against the symmetric position of it, which is this one. But we will not check the middle one. What we want is to check the middle one and consider the symmetric position of it just the same value basically. And so if we do this +1, it would work here, right? There will be maybe 1 repetition comparison, but that's fine. And so here, after doing that, we can just take the number in the opposite like direction here. So for example, which we said is n-i-1. And now we can check what we said here. So it should be either the same, and so what I'm going to do is first just write the condition, which is same and r 0, 1, or 8, right? So in order to do that, we're going to check number at I is equal to number j, and it's either 0, 1, or 8. And the other condition is if it's not this, then what we want is the OR condition is one of them is 6 and the other is 9. And so to express that, we can just take nim I plus nim j. If one is 6 and the other is 9, then it's either 6, 9 or 9, 6, right? And so we do that. Okay, so if this is correct, then that's, as long as this is correct for all elements in num, for all the values in num, then the number is a strobogrammatic, right? But if we find only one occurrence where that's not the case, then that means if you rotate 180 degrees, we will not get the same number. And so we will check if this property doesn't work at any point, we can just return false. Now, if we go through the entire thing and it still works for each one of them, that means all of them verify this property, then we can just return true at that point. So let's check here. So we have a problem, right? So we have a problem somewhere. Let me just put parentheses just to make sure that that's not the reason. Yeah, that was the reason, because not was done only on this portion of the condition. Okay, so now let's try a couple of things. So for 1, for example, let's try for 0, 1, which shouldn't work because 0 doesn't match the number in the symmetric position, which is 1. So that works. And what can we try else? We can try, just to be sure, 11 should work. Let's take a number here. Let's take this one. So this one should return true. Okay, so it sounds like it should work. So let's submit this. Okay, so that passes. Now, we can write it this way, but Python has this useful thing called all, where it can check a condition is true. So it returns true if the condition is true for all values in an iterable. So we want to check that for all values in the iterable, which is this num here. So the way we can do that is we can keep that n equal to this length, and we can return, basically we can do all. We want the number at the position to be equal So we are just going to repeat our condition that we wrote earlier. So let me just take it here. So let's take this condition that we want to be always true. And so we are going to return all. Just comment this part here. And the condition needs to be this here. And we want that to be for I. And that's about it. So let's clean this up a little bit. Since I did this, I can't use J, so I need to do this. And so that would mean, and this is true for that. Okay, so this should work fine. Yeah, so it passes. So one nice trick for, instead of writing this lengthy n minus I minus 1, is to use, so Python has this property where if we have, say, an array of, let's say we have an array of 1, 2, 3, 4. If we do array 1, that gives us the number at this position. If I do array minus 1, that gives me the number at this position. But if I do minus 2, that gives me this number. So let me just take an array that is bigger so that it can be more clear. So 6, 7, 8, 9, right? So if I take the element at 0 position, right? So what's the length of the array here? That's 9. Now if I take array minus 9, that's the first one, right? But if I take minus 8, yeah, so what am I going with this basically? So if n is the length of the array, right? And I equal to 2. What is n minus I minus 1? That's 6, right? So 0, 1, 2, 3, 4, 5, 6. So that should give us array of n minus I minus 1. That's 7, right? And array of I, that's 3. So 3 in its symmetric position on the other side is 7. So another way to get so n minus I minus 1 is 6. We can get it either by doing this, or we can get it by doing minus 3, right? So array of minus 3 give us 7, right? And so basically minus 3 is what? It's actually just minus I. So our I here is 2. Minus I minus 1, that's minus 3. So in Python, basically for the indices here, minus 3 is equivalent to n minus 2 minus 1. Yeah, this is false here, but yeah, it's equivalent. And so in order to do this, minus 3 here, which is just minus I minus 1. So with Python, minus I minus 1 will give us minus n minus, will give us this value here. So I can either replace this with this, and it will work super fine. So it still works the same way. It's still, if I use this, let's say this, it still works fine. So in Python, this here, this here is equivalent to, for indices, if you take that as an index, you'll get the same value. So basically this here is the same as getting it this way. So if let me submit this to show you that it's the same thing. So it's the same thing. Now, a simpler way to get minus I minus 1 is to just use this I. So you can see it's minus 3. Let me show you a couple of examples. If we do minus 4, then this is minus 5, and this is minus 5. And if you take, let's say 12, this is minus 13, and this is minus 13. So it's actually the same value. This here is equivalent to doing this. So we can make our code here a lot shorter by just doing this. So remember basically that the gist of this is that if you want to get the value at the symmetric position to I, you can just use this. And that's all there is to it. So let's submit this and see. Okay, so the solution passes there. Now I'm going to try to write it in another even simpler way, which is, so if we let's take the same thing and let's go, let me just keep the formula that we did here. Okay, so how are we going to write this differently? So the one thing to notice is that what we are looking for is that the number is the same and in one of these. What does this condition mean? Well, this condition means that we are looking for either 0, 0 or 1, 1. The values needs to be the same and needs to be in this, right? Or 8, 8, right? So those are the values that we are looking for. Now, what does the other condition mean? So this condition means that we are looking for values that are in 6, 9 or 9, 6. But these values is the same as looking for values in 6, 9, 6, right? Because contains checks the entire thing. So if it's this one, then we will find it as this part. If it's this one, then we will find it at this part, right? So what this means is that basically that instead of checking all of this, we can check that the value at I plus the value at the symmetric position are in these values here and this one. So if it's in any of these, that means that we found our case of what we want. But if it's not, then that means that we have a mismatch there and we can return false. So let's just then implement that. So this is in the range of the same thing we did earlier, and then we can check if name of I plus name of this I is in. If it's in, then that's good, but if it's not in it, then we can return false. And so we can just do that by adding a space so that it matches only the occurrence of these, right? So this is basically, we can do that, or we can do something like this also. This also would work, so we can do this. This also will work fine, but I just prefer doing this 1, 1, 8, 8, 6, 9, 6. Actually, this won't work fine. If we do the list, we will need to do it like this. But with the string, since it checks all substrings, it works. So yeah, so we can do this, and then if it's not in it, so that means it doesn't verify our condition, we can return false. Now, otherwise, if we go through all of them and it's the conditions are valid, then we can return true. So let's run this. Submit this. Okay, so that passes. Now, okay, so we did this. We remember earlier we did a for loop and converted that to using all here. So let's do the same thing. So that means that we can just bring this up and keep this and just replace our condition here. So the condition is this instead of this whole thing. And so we can just return this right away instead of doing the for loop. So all of them, we want this condition to be true. And so we want it to be true, so we say in. And we do the same thing. So if this is true, the condition is true, then for all of them, then it's a strobogrammatic number, right? And so let's just run this and submit. Okay, so that passes. Now this here we can rewrite it in yet a different way. So we can keep the condition, but just instead of doing this, we can just another way to obtain the symmetric things. So let's say we have this number 1, 2, 3, 4, right? If we zip the number with its reverse, so which is this one. So let me just say first that if you do this in Python, you will get the reverse, right? So what is the zip of the number and its reverse? So that just zips each number with the number in the symmetric position, because you can see 1, 2, 3, 4. So if I do this, so number is this, and the reverse is this. So it zips basically 1 with 4, 2 with 3, and 3 with 2, and 4 with 1, which is basically just zipping 1 with 4, 2 with 3. So each number with its symmetric position, and that's what it does. Of course, it's duplicating a little bit, but that's fine with this part here, but that's fine. And so we can just, instead of going through the half here, we can check that C plus D are in that. And what is C plus and D? Those are the values in the symmetric position, which means, which we said that we can obtain by doing this zip, right? So we can just say for C and D in the zip that we mentioned, right? And that should basically be all we need, and we no longer need to check that. And this should work fine too. Yep, it does. Okay. So yeah, that's another way of writing it. Okay, so now let's try a different approach. So not at all in the same way as checking this, which is it's also a clever idea. It is a clever idea. So let's see. So what do we have? So we know that 9 multiplied. So we know that we want the values that are either 0, 0, 1, something like this in the symmetric positions. We still want that. So symmetric positions means, so values in symmetric positions should be that, or 9, 6, or 6, 9, right? So it should be one of these. So what are the product of these, right? So the products of these values, which means basically the product of 0 and 0. So the product of 0, 0, basically that's 0 multiplied by 0. That's 0, right? So I'm just going to observe something here. So the products of these, what are they? The product of 1, so 1, 1, that's 1 multiplied by 1, that's 1, right? And 8 multiplied by 8, that's also something we can check here. So 8 multiplied by 8, that's just 64, right? So that's just 64. What's 6 multiplied by 9? That's the same as 9 multiplied by 6, right? So that's basically works for both, right? So, and that's 6 multiplied by 9, that's 54. Okay, so what does this mean? That means that instead of checking these, we can just check the products for the value. So for a number like this, we can check the product of this with this, and then recurse. After checking that it matches one of these, we can recurse and check the value of this and the one in the symmetric position, and then we keep doing that, and we check for this one. And then once both pointers, let's call them low and high, like low and high, once both pointers like reach each other, or one of them high become bigger than L, so if high becomes bigger than low, then at that point we can just exit, right, with true, because that means while we keep checking the product and it's valid, and we get here and it's still false, we didn't encounter one where it's not one of these, then we can just return false. There is only one thing we need to take care of. So for 0, the problem is that if it's 0, 6, the product will be still 0, but this number is now a valid strobogrammatic number, so we need to handle that. So let's just keep that in mind. And so let's define here a helper function that will help us doing this. And so what we said is we will pass the pointers, the pointer at this position and the pointer at its symmetric position, right? So that would be lower and higher. And as soon as we reach the point where lower is now, sorry, this was lower, high. This is when the low value, like, so when this pointer like becomes here, so, and that basically means we are done, we checked all values, right? So if that's the case, then we can just return true, because we are done, we didn't find a value that doesn't match the conditions. Otherwise, we are going to take the product of, so that we can get this and check the product. So we are going to take the product of the number at the low position with the number at the high position, okay? And we want to check if that product is, so we don't want to check 0 because of this problem here, but we can check 1, we can check 64, we can check 54. 54 takes care of all of these, of 69 and 96. So 1, 64, and 54. Or let's handle the product case. If the product is equal to 0 and both values are equal, that means that both of them are 0. So this case, then yes, we want to handle it. But if both of them are not equal and the product is 0, that means one is 0 and one is not 0, and we don't want that to be valid, right? So that's why we check product equal to 0 and the numbers are equal. And so if this is the case, that means that we have a valid combination of two symmetric numbers, and so we can continue. So the way we continue is just we can recurse and just increase low and decrease high, so that they can end up converging, and we can finish when we are done here. And then we can return false if this condition was not valid, right? So at that point we can just return false. Let's run this. Okay, so it's returning null because I didn't call helper for the initial call. So for the initial call, we want to call helper with nym, and as low just 0 and as high just the length minus 1, which is basically just taking the first number and the last number, and those are in symmetric position, right? So let's run this and let's submit it. Okay, so that passes. Yeah, so that's it for now. Yeah, see you next time. Bye.